Hello, Dr. Buzz here. Today we'll be covering part 1 of my linear algebra review for computational chemists. In this video, we'll be covering vectors and matrices. You can think of vectors as one-dimensional lists of numbers, and they can be represented by an arrow that starts from the origin, as shown on the graph on the right. And they can have any number of entries, and the number of entries in the vector is called the dimension. So a 2D vector would have 2 entries, and we call that an element of R2. A 3D vector will have 3 entries, and we call that an element of R3. And a 7D vector would have 7 entries, and we call that an element in R7. The length of a vector is given by the formula on the middle of this page. Say you have a vector A with entries A1, A2, AN. That means the length of A is just A1 squared plus A2 squared plus every entry squared, all that square rooted. And this is derived from the Pythagorean theorem. Now, an important operation between two vectors is a dot product, where A dot B is A1 B1 plus A2 B2 plus AN times Bn, where A1 and B1 are the corresponding elements in the vectors A and B. And based on this definition, you could show yourself that the length of a vector is actually the square root of a vector's dot product with itself. And matrices are just two-dimensional lists of numbers that represent linear transformations of one vector onto another. And the definition of a linear transformation is one that satisfies this property. When the operator A acts on C1U plus C2V, or C1 and C2 are scalar constants and U and V are vectors, and the result is C1 times A operated on U and C2 times A operated on V. And the columns of a matrix A that represents that transformation represents what each basis vector E1 all the way to En become after their transformation acts on it. An example of basis vectors in the 3D case is E1 is just 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. So we can give an example of this by rotation by 90 degrees counterclockwise in R2. So the vector E1 is 1, 0, and once you rotate that vector 90 degrees counterclockwise, we represent that vector as AE1, and that'll just be 0, 1. We could do the same for E2, which is originally 0, 1, but once you rotate it 90 degrees counterclockwise, it becomes AE2, which is negative 1, 0. Since AE1 is 0, 1, and AE2 is negative 1, 0, the matrix A, the columns of it can be represented by AE1 and AE2. So the matrix A is just 0, 1, negative 1, 0. Or 0, negative 1, 1, 0, reading row first. And to rotate any vector in R2 by 90 degrees counterclockwise, you have to multiply the matrix A to it. Since we haven't defined what a matrix vector product is yet, let me define it. So the matrix A times the vector X is just, if you represent a matrix A by the column vectors A1, A2, all the way to AN, and the entries of X as X1, xn, that means A times X is just a vector X1, A1, plus X2, A2, plus xn, AN. And we call this a linear combination. And notice that for this definition to be well defined, A must have n columns, which is equal to the number of entries of X. And the matrix product is defined similarly, where if you have A times B, it is equal to A times B1, B2, all the way to Bn, where B1 to Bn is B represented as column vectors. So that will just be A. So the first column of the result of A times B is AB1. The second column is AB2. And the nth column is ABN. And you could think of those kind of like parallel matrix vector products. Or another way to think about it is if you represent A as a bunch of row vectors and B as a bunch of column vectors, each entry in the result is just a dot product of the corresponding row vector of A times the corresponding column vector of B. And notice that the number of row vectors A has and the number of column vectors B has does not have to be the same. However, one thing that does have to be the same is that the dimension of every row vector in A has to be equal to the dimension of every column vector in B, which is the same thing as saying the number of columns of matrix A has to equal the number of rows of matrix B. So if you have A as an m by n matrix, where m is the number of rows and n is the number of columns, and B is an n by p matrix, that means the product will be an m by p matrix. Well, that's all for today. Have a great rest of your day.